In 1987, inside the mud-brick pyramid complex of Huaca Rajada on the arid northern coast of Peru, archaeologists opened the undisturbed funerary chamber of the Lord of Sipán. Wrapped inside layers of sacred textiles lay an astonishing array of ceremonial regalia, massive crescent headdresses, intricate ear ornaments, face masks, and layered breastplates that gleamed with the unmistakable yellow brilliance of solid gold. To the naked eye, this 7th century Moche ruler was entombed in pure, unyielding treasure. Yet beneath that luminous facade lay a profound metallurgical paradox. When conservators began examining the unlooted artifacts, they discovered bright green crusts of copper salts erupting directly through what appeared to be an unbroken, perfect sheet of gold. Microscopic cross-sections soon confirmed the impossible. These grand royal ornaments were not solid gold. They were over 80% base copper, encased in a continuous, atomically bonded outer skin of pure gold, less than a single micron thick. It was thinner than a strand of silk, yet it conformed seamlessly to every delicate crease, edge, and hammered relief. In old-world metallurgy, applying a gold veneer of this uniformity typically required either mechanical leaf gilding, which leaves visible seams and flaking edges, or toxic mercury amalgam paste. Neither technique was used here. In modern industrial engineering, depositing an ultra-thin, seamless gold layer onto base copper requires electroplating, driven by chemical batteries, dynamos, and controlled electrical currents. Yet the metalsmiths of northern Peru perfected this exact electrochemical bond more than 1,000 years before European scientists developed the first battery. How did ancient Andean smiths dissolve noble gold and deposit its atoms onto base metal without electrical power, wires, or modern chemical apparatus? The answer begins with a bizarre archaeological crisis: gold ornaments that seemed to rot from the inside out the moment they met the open air. When conservators first began stabilizing artifacts recovered from high-status tombs across northern Peru, they encountered a phenomenon that contradicted standard conservation experience. Gold is the most noble and chemically inert of all metals. It does not tarnish in air, rust in moisture, or react with common environmental salts. Yet when these seemingly pristine gold headdresses, masks, and nose ornaments were brought into museum laboratories, many began to swell, warp, and crack from within. In severe cases, microscopic fissures split across the lustrous surfaces, venting a fine, powdery green efflorescence that pushed outward like pressure fractures in ice. The paradox resolved only when conservators placed damaged fragments under metallurgical microscopes and prepared cross-sectional mounts. Beneath an exterior that gleamed like solid bullion, the structural interior of the metal was almost entirely gone. Over centuries buried in coastal desert sands, moisture and chlorides had penetrated the microscopic pores of the objects, slowly converting an internal core of base copper into cuprite, tenorite, and hydrated copper carbonates like malachite. Because copper minerals occupy a significantly larger physical volume than metallic copper, this internal mineral expansion exerted massive outward pressure, ultimately bursting the golden exterior from the inside. Scanning electron microscopy revealed the precise physical anatomy of this failure. The gold skin was not a thick outer cladding or an independent casing. It was an astonishingly uniform layer measuring between 0.5 and 2 micrometers thick, equivalent to less than a 50th of the diameter of a human hair. Despite its microscopic profile, the layer was continuous and completely integrated with the underlying metal. It did not display the microscopic air pockets, hammer overlap seams, or uneven thickness variations that inevitably occur when a metalsmith wraps a base metal core in hammered gold foil. Mechanical wrapping at 2 micrometers is physically impossible without tearing, yet here the golden layer traced every microscopic ridge, cast depression, and hammered contour with absolute precision. The structural evidence was undeniable. The Moche and their predecessors had not assembled these objects by physical joining. They had somehow created an unbroken, sub-micron envelope of pure gold across complex 3-dimensional copper forms. The immediate question facing archaeometallurgists was whether the artisans had used an established old-world chemical method or an entirely separate branch of metallurgical science. In European and Asian metallurgical history, applying an ultra-thin, durable gold coating to base metal without mechanical foil wrapping relied almost exclusively on 2 distinct traditions: leaf gilding and fire gilding. Leaf gilding was an adhesive or mechanical process where gold was beaten between animal membranes into gossamer leaves and applied to surfaces using organic glues, egg white glares, or heated bitumen. While effective on stone and wood, leaf gilding on metal produced fragile mechanical bonds. Under microscopic scrutiny, leaf-gilded artifacts show clear lateral seams, uneven overlapping margins, and a distinct tendency to delaminate along stress planes whenever the underlying metal flexes or corrodes. Fire gilding, perfected in ancient China and widely adopted across the Roman world, was a far more robust chemical method. Artisans dissolved gold in liquid mercury to create a buttery amalgam paste, spread this paste over clean bronze or copper, and subjected the object to intense heat. The mercury vaporized at around 350 degrees Celsius, leaving behind a fused layer of gold that could be burnished to a mirror sheen. Fire-gilded statuary exhibited exceptional adhesion and could conform to intricate cast relief without seams. However, the chemical thermodynamics of fire gilding leave behind an inescapable forensic fingerprint. Mercury never evaporates completely. Even after intense heating and centuries of burial, fire-gilded metal retains between 8 and 25% residual mercury trapped within the crystalline lattice of the gold veneer. When researchers ran quantitative spectroscopy and electron probe microanalysis on gilded sheet metal from Sipán and Vicús, the results eliminated both old-world paradigms. The Andean coatings contained 0 detectable traces of mercury, completely ruling out amalgam fire gilding. Simultaneously, the microscopic interface between the gold and copper showed no organic adhesives, no mechanical overlaps, and no seam lines, even around razor-sharp 90-degree bends and complex filigree cutouts. Where a Roman gilded bronze statue shows a thick, slightly irregular amalgam crust anchored by mercury fusion, a Vicús nose ornament exhibits an atomically thin, uniform envelope that behaves as a single metallurgical unit with the substrate. The Andean smiths had achieved the seamless fidelity of chemical gilding without mercury and the microscopic thinness of gold leaf without seams. To understand how they achieved this, metallurgists had to look not at pure metals, but at the foundational alloy system of South American metalworking. Long before Andean smiths mastered the chemistry of pure copper surfaces, they spent centuries exploring the properties of a specialized ternary alloy that early Spanish chroniclers called tumbaga. Tumbaga is not a single fixed recipe, but a deliberate metallurgical system combining copper, gold, and frequently silver across a broad range of elemental ratios. While modern industrial metallurgy often treats copper-gold mixtures as simple structural dilutions, Andean metalworkers developed tumbaga because its mechanical, thermal, and chemical properties were uniquely suited to their manufacturing methods. Pure copper melts at 1084 degrees Celsius, while pure gold melts at 1064 degrees. When these two metals are alloyed together, the metallurgical phase diagram reveals a pronounced eutectic depression. At an alloy composition of roughly 82% gold and 18% copper by weight, the melting point drops by nearly 200 degrees, down to 910 degrees Celsius. Adding small fractions of silver lowers the melting threshold even further while significantly reducing molten viscosity. For ancient artisans working with charcoal hearths and blowpipes rather than mechanical bellows, this lower melting point meant alloys could be melted and cast into complex, thin-walled molds with far greater fluid flow and dramatically fewer structural casting voids. Beyond its thermal advantages, tumbaga altered the mechanical behavior of sheet metal. Pure gold is exceptionally ductile but lacks mechanical spring, deforming permanently under minimal load. Pure copper work hardens rapidly during hammering and becomes brittle unless continuously annealed. Tumbaga combined the ductility of gold with the structural rigidity of copper, allowing smiths to hammer ingots into ultra-thin, resilient sheets that could vibrate, flex, and hold crisp, embossed sculptural relief without tearing or collapsing under their own weight. This material served an equally profound ideological purpose in Andean cosmology, where gold embodied the radiant generative energy of the sun and silver represented the cool, reflective power of the moon. By combining copper, gold, and silver into an indivisible metallic matrix, artisans created an alloy that unified these symbolic forces within the very body of an object. Yet despite containing significant amounts of base copper, finished tumbaga regalia exhibited surfaces of brilliant, unblemished gold. The secret lay in an ingenious subtractive chemical process known as depletion gilding. Depletion gilding, historically termed mise en couleur, is a subtractive surface enrichment technique that transforms an alloy containing modest amounts of gold into an object with a pure gold exterior. Instead of adding gold to the surface, the metallurgist selectively removes base metals from the outer atomic layers of the alloy, leaving the unreactive gold behind as a continuous surface crust. The process begins with a cast or hammered object made from low-carat tumbaga, often containing as little as 10 to 30% gold, with the remainder consisting of copper and silver. The smith places the object into an open charcoal fire to anneal the metal. Under high heat and atmospheric oxygen, the copper atoms at and near the surface react aggressively with oxygen to form a black and red crust of copper oxides, primarily tenorite and cuprite. Gold, being chemically inert, does not oxidize and remains locked within the metallic matrix beneath the scale. Once cooled, the oxidized object is immersed in a corrosive pickling bath. Andean artisans did not possess distilled mineral acids like sulfuric or nitric acid, but they had access to potent organic acids derived from the concentrated juices of local plants, such as oxalis, as well as aqueous slurries of naturally occurring mineral salts like alum and ferric sulfates. These acidic pickling solutions selectively dissolve the brittle copper oxide scale, while leaving the metallic gold and unoxidized alloy completely unattacked. When the object emerges from the bath, the surface copper has been stripped away, exposing a microscopic, highly porous sponge of pure gold. Because a single heating and pickling cycle removes only a few atomic layers of copper, the initial surface appears dull, patchy, and brownish. The smith repeats the entire cycle multiple times, heating to oxidize more copper from just below the depleted zone, quenching and pickling in the acid bath. With each successive pass, the depletion zone deepens, and the concentration of pure gold on the surface increases. Once the porous gold layer reaches sufficient thickness, the artisan uses smooth hematite or polished stone burnishers to mechanically collapse the microscopic gold sponge, consolidating it into a dense, mirror-bright surface that looks indistinguishable from solid gold bullion. Depletion gilding was a triumph of chemical control, but it had an absolute physical prerequisite. The core metal had to contain gold from the very beginning. When archaeometallurgists turned their attention back to the elite artifacts of the Moche and Vicús cultures, they discovered objects that shattered the boundaries of depletion gilding entirely. intricate royal regalia made of solid, unalloyed copper that bore the exact same sub-micron skin of pure gold. When archaeometallurgists conducted destructive cross-sectional assays on collections of Vicús and Moche sheet metal objects, the numbers refused to align with the laws of depletion gilding. Quantitative core sampling of large ceremonial pectorals, nose ornaments, and hammered plaques revealed base metal purities exceeding 98 to 99% elemental copper. The internal matrix contained only negligible trace elements of lead, arsenic, and iron, with gold concentrations hovering near absolute zero. This single metallurgical data point demolished the depletion hypothesis for this entire class of artifacts. In depletion gilding, the final gold skin is not an addition, it is an arithmetic remainder. If a smith begins with an alloy of 12% gold and dissolves away 88% of the surrounding base metal, the surface is enriched because the gold atoms were already physically distributed throughout the crystal lattice. On an ingot of solid copper, no amount of heating, oxidizing, and acid pickling can ever produce a gold surface. Stripping copper from copper merely leaves less copper. To produce a continuous, pure gold veneer on an object composed entirely of base metal, every single atom of gold visible on the exterior had to be introduced from an external source. Yet the structural puzzle only deepened under microstructural examination. The gold on these unalloyed copper sheets did not sit on top of an adhesive binder, nor was it mechanically anchored by hammering foil into carved grooves. Optical micrographs revealed that the gold layer, measuring barely 1 micrometer in thickness, traced every single microscopic valley, grain boundary, and hammer mark of the underlying copper with atomic precision. The contact zone between the two metals was perfectly continuous, exhibiting no voids, no solder alloys, and no mechanical deformation zones typical of leaf gilding. The implications were profound. To achieve this result, ancient northern Peruvian artisans could not have relied on dry pyrometallurgy or mechanical fabrication alone. They had to be manipulating gold in an entirely different physical state. The metal had to be carried in a liquid medium, dispersed as individual ions or soluble complexes, and transferred onto the solid copper through an intentional chemical reaction. For 19th and 20th century, historians accustomed to attributing the invention of chemical plating to European scientists like Luigi Brugnatelli in 1805, the existence of atomically bonded gold coatings on pre-Columbian copper created a profound technological paradox. The breakthrough that resolved this historical paradox began in the early 1970s in the laboratories of the Massachusetts Institute of Technology. Professor Heather Lechtman, a pioneer in the emerging discipline of archaeometallurgy, founded a systematic research program dedicated to decoding Andean materials science. For generations, traditional Eurocentric scholarship had treated ancient South American smiths as intuitive metalworkers who operated by accidental discovery, lacking the theoretical rigor of Old World metallurgy. Old World traditions had prioritized the development of hard, utilitarian alloys like bronze and iron for tools and weapons, casting Andean metallurgical traditions as merely decorative and conceptually primitive. Lechtman rejected this dismissive framing, examining hundreds of pre-Columbian metal samples under scanning electron microscopy and electron microprobe analysis. She observed a degree of surface control, chemical consistency, and reproducibility that could not be explained by random craft accidents. Her laboratory notebooks documented that Moche and Vicús metalsmiths were deliberately engineering the surface chemistry of their regalia, demonstrating an intimate empirical mastery over the behavioral properties of complex mineral solutions. In 1979, Lechtman published her landmark paper, Pre-Columbian Surface Metallurgy, in the journal Science. In it, she formulated a revolutionary hypothesis. more than 1,000 years before the development of modern electrical chemistry, ancient Andean artisans had developed a true wet chemical, electrochemical displacement plating technology. Rather than relying on external power sources, wires, or galvanic batteries, they utilized the intrinsic chemical energy stored within natural minerals and the galvanic potential difference between dissimilar metals. To prove her hypothesis, Lechman did not merely analyze ancient fragments. She set out to reconstruct the ancient chemical systems using only the raw materials, tools, and mineral reagents that were geographically and historically accessible to pre-Columbian coastal societies. Her work demonstrated that what modern science classified as electrochemistry had been discovered, refined, and deployed on an industrial scale along the Andean coast through a sophisticated, empirical chemistry based entirely on native desert minerals. The foundation of this ancient chemical industry lay in the unique geology and hyper-arid climate of northern Peru. The coastal strip running between the Pacific Ocean and the western slopes of the Andes, encompassing the Chicama, Lambayeque, and Piura valleys, is one of the driest landscapes on Earth. Over geological epochs, mineral-laden runoff from the high Cordillera leached down into the coastal basins, where extreme evaporation rates prevented the salts from washing into the sea. Instead, they crystallized into massive evaporite beds, saline crusts, and mineral outcroppings that served as an extensive natural chemical pharmacy. Foremost among these raw materials was potassium nitrate, known locally as saliter or saltpeter. Formed in nitrogen-rich desert soils and dry cave floors, potassium nitrate provided an abundant source of powerful nitrate oxidizers. Interspersed with these nitrate beds were vast deposits of halite or common sodium chloride, crystallized in coastal salt pans and inland dry lakes. Equally vital were the complex hydrated sulfate minerals found weathering out of copper-rich hydrothermal veins in the Andean foothills. Ancient prospectors gathered bright blue chalcanthite, a naturally occurring hydrated copper sulfate, alongside copiapite, a brilliant yellow basic ferric sulfate, and potassium aluminum sulfate, commonly known as alum. When mined and dried, these minerals formed shelf-stable, crystalline salts that could be ground into fine powders, measured in precise volumetric ratios, and transported across metallurgical workshops. In their dry crystalline state, these compounds are relatively inert, but when combined in warm water inside ceramic vessels, the mineral mixture undergoes immediate dissolution and chemical reorganization. The hydrated sulfates release hydronium ions, turning the bath sharply acidic. The saltpeter dissolves into mobile potassium and nitrate ions, while the halite contributes a high concentration of free chloride ions. Without access to distilled industrial liquid acids like modern hydrochloric or nitric acid, ancient Andean metallurgists had synthesized an aggressive, highly acidic, oxidizing electrolyte solution using nothing more than crushed desert stones and water. Dissolving metallic gold is one of the most demanding challenges in inorganic chemistry. Elemental gold possesses an exceptionally high positive standard reduction potential of +150 volts, making it one of the most chemically noble elements in existence. It resists attack from virtually all concentrated single acids, sulfuric acid, hydrochloric acid, and nitric acid on their own leave metallic gold completely untouched. In modern laboratory practice, dissolving gold requires aqua regia, a fuming, corrosive mixture of concentrated nitric acid and concentrated hydrochloric acid, operating through a simultaneous two-part reaction. The ancient Andean mineral bath achieved this exact chemical feat through an elegant thermodynamic balance. When artisans introduced finely hammered gold foil or native gold dust into their aqueous mixture of potassium nitrate, sodium chloride, and alum, a complex multi-stage equilibrium was established. The acidic sulfate environment created by the alum and ferric sulfates provided the low pH necessary to activate the nitrate ions. In this acidic medium, the nitrate acts as a powerful oxidizing agent, stripping electrons from the neutral gold atoms at the surface of the foil. However, oxidation alone is insufficient to keep gold in solution. As gold atoms lose electrons to become auric cations, the reaction quickly stalls because the energetic barrier to sustain free gold ions in water is unfavorable. This is where the chloride ions from the dissolved halite play their decisive role. The free chloride ions immediately surround the newly oxidized gold cations, forming exceptionally stable coordination complexes known as tetrachloroaurate ions. By complexing the gold into soluble anionic coordination complexes, the chemical bath drives the equilibrium forward, continuously pulling more metallic gold off the solid foil and into aqueous solution. Laboratory tests replicating Lechman's mineral ratios confirmed that by gently heating this mineral slurry near the boiling point of water, ancient smiths could fully dissolve several grams of solid gold foil within a few days. The result was a clear, slightly amber, gold-bearing aqueous electrolyte, completely devoid of particulate gold and perfectly primed to react with metallic copper. When an artisan dipped a freshly burnished, grease-free copper sheet into this amber electrolyte, an immediate electrochemical reaction occurred right at the interface between the metal and the liquid. To understand why gold began plating onto the copper instantaneously without any external battery, we have to look at the relative chemical reactivity of the two metals expressed in the standard electromotive force series. In electrochemical terms, every metal has a characteristic standard reduction potential, which measures its tendency to acquire electrons and reduce to a metallic state. Metallic copper has a standard reduction potential of positive 34 volts for its divalent ion. Gold, in contrast, sits far higher on the nobility scale, with a standard reduction potential of approximately positive 50 volts for auric ions in standard aqueous solutions. This substantial voltage gap of over 1 volt creates a powerful, spontaneous thermodynamic drive. In chemical terms, gold possesses a vastly greater affinity for electrons than copper does. Gold ions in solution want electrons, and metallic copper atoms are energetically favored to give them up. As soon as the solid copper object enters the mineral bath, the copper atoms on its outermost atomic surface begin to oxidize spontaneously. Each copper atom sheds electrons into the bulk metal substrate and dissolves into the aqueous bath as a soluble copper ion. This process releases a steady stream of free electrons directly within the conducting copper sheet. Simultaneously, the dissolved tetrachloroaurate coordination complexes resting against the metal surface encounter this influx of electrons. The gold cations within the chloride complexes instantly absorb these electrons at the solid-liquid boundary. As each gold ion gains 3 electrons, it reduces from a dissolved, charged complex back into a neutral, solid gold atom. Because this electron transfer takes place directly on the surface of the copper sheet, the newly created gold atoms deposit immediately onto the copper lattice, nucleating and adhering to the metal. This process is known in modern metallurgy as galvanic displacement or cementation. What makes the technique so brilliant is that no external wires, electrodes, or modern power sources were necessary. The solid copper ornament acted simultaneously as the electron donor, the electrical conductor, and the physical substrate for the plating. The energy driving the entire electroplating process was stored entirely within the chemical bonds and the electrochemical potential difference between the dissolved desert salts, the gold ions, and the metallic copper itself. If a copper sheet continuously sheds electrons and dissolves while gold continually precipitates onto its surface, it might seem logical that the reaction would simply continue until either the gold in the bath was exhausted or the copper dissolved completely into sludge. Yet when archaeologists analyze cross-sections of authentic Moche and Vicús gilded ornaments, they do not find thick, irregular crusts of gold. Instead, cross-sectional micrographs consistently reveal a remarkably uniform, paper-thin gold veneer that measures between 0.1 and 1.0 micrometer in thickness. This precise micro-scale uniformity was not the result of the artisan manually pulling the object out at a lucky moment. It was governed by a fundamental, self-terminating physical threshold built into the mechanics of displacement plating. For galvanic replacement to operate, bare copper atoms must maintain continuous, unhindered physical contact with the aqueous electrolyte. As the reaction begins, gold atoms precipitate at discrete microscopic nucleation sites across the copper surface. Within minutes, these individual gold islands grow and merge, spreading outward into a continuous metallic blanket. As this mantle coalesces across the exterior of the ornament, it gradually seals off the underlying copper from the surrounding liquid. Once the newly deposited gold layer reaches a continuous thickness of just a fraction of a micrometer, the electrolyte can no longer touch the base copper underneath. The dense mantle of solid gold acts as an impermeable barrier. Because the copper atoms are physically sequestered from the bath, they can no longer oxidize or release electrons into the solution. Without a continuous supply of electrons flowing across the metal-liquid boundary, the reduction of dissolved gold ions abruptly stops. The reaction effectively turns itself off. This self-limiting property explains why hundreds of distinct copper ornaments recovered from northern Peruvian tombs share virtually the exact same microscopic veneer profile. Whether the object was a tiny bead, a wide pectoral, or a complex feathered headdress, the physics of displacement plating naturally produced a flawless, sub-micron coating that conserved precious noble gold while achieving a visually indistinguishable golden surface across every microscopic contour. Achieving this smooth, microscopic layer was far from straightforward. In modern laboratory reconstructions at the Massachusetts Institute of Technology, metallurgists encountered a severe chemical obstacle when attempting to replicate the process using raw, unadjusted mineral baths. If an artisan took the acidic mineral digest immediately after dissolving the gold foil and dipped a copper sheet directly into it, the result was an absolute disaster. Because the mineral slurry required strong acidic conditions to break down the gold foil into tetrachloroaurate ions, the unbuffered solution contained high concentrations of aggressive free acid. When bare copper was submerged in this strongly acidic bath, the acid attacked the copper violently. Instead of a slow, orderly transfer of electrons, the acid dissolved the copper into copper salts at a catastrophic rate, venting gas and deeply pitting the surface. The gold that did manage to precipitate came down as a coarse, dark, spongy sludge that sloughed off at the slightest touch, leaving behind a ruined, corroded sheet. To overcome this, ancient Andean metallurgists developed a crucial intermediate step in their empirical protocol: solution neutralization and chemical buffering. Through systematic trial, Heather Lechtman demonstrated that ancient smiths neutralized the excess mineral acidity prior to dipping the copper ornaments. They achieved this by adding alkaline reagents, most likely leached wood ashes containing potassium carbonate, or naturally occurring evaporite minerals such as sodium bicarbonate. By carefully introducing these alkaline agents into the warm gold bath, the artisans raised the pH of the electrolyte, neutralizing the aggressive free acids while keeping the gold coordination complexes stable in solution. When Lechtman tested these buffered solutions, the dynamics of the bath shifted entirely. The destructive, rapid acid etching was completely suppressed. In this balanced, mildly acidic to neutral environment, the copper dissolved at an exceptionally slow, controlled rate, governed strictly by the galvanic potential difference between copper and gold. Instead of forming a dark, ragged sludge, the reduced gold atoms laid down in an ultra-fine, tightly packed crystalline lattice, creating a coherent, highly reflective, mirror-smooth metallic coating across the entire copper ornament. Even after achieving a smooth, buffered galvanic deposit, the gilded ornament was not yet finished. At this stage, the newly formed gold layer was purely a mechanical deposit held against the copper substrate by weak surface adhesion. Under high magnification scanning electron microscopy, this freshly plated chemical layer appears as a delicate microcrystalline aggregate. In its raw state, the gold veneer was fragile. If handled roughly, burnished aggressively, or bent during subsequent metalworking, the microcrystalline gold could easily flake or shear away from the copper core. To transform this delicate chemical veneer into a durable, permanent metallurgical bond, ancient Andean metalsmiths introduced a critical final step: low-temperature thermal sintering, also known as atomic diffusion welding. The plated copper object was carefully removed from the mineral bath, rinsed clean of residual salts, and placed into a gently heated annealing hearth fueled by charcoal. The artisans raised the temperature of the object to approximately 500 to 700 degrees Celsius. This temperature range was chosen with precise empirical intent. It was hot enough to activate atomic movement, yet well below the melting point of pure copper at 1084 degrees Celsius, the melting point of pure gold at 1064 degrees, and safely below the tumbaga copper-gold eutectic threshold of approximately 800 degrees. At these elevated temperatures, thermal energy excited the crystal lattices of both metals right at their boundary. In a process governed by solid-state thermodynamics, copper and gold atoms began to migrate across the physical junction. Copper atoms diffused outward into the base of the gold layer, while gold atoms diffused inward into the copper substrate, interpenetrating each other's crystal structures. This solid-state interdiffusion formed a continuous, microscopic metallurgical bridge across the interface. The thermal treatment also caused the porous, individual microcrystals of the plated gold to fuse together, eliminating microscopic voids and forming a dense, uniform metallic skin. Once cooled, the gold was no longer merely resting on the copper. It was atomically interlocked with the substrate. The resulting composite sheet was remarkably tough and ductile, fully capable of being hammered, folded, embossed, and polished without the gold skin ever separating from its copper core. This metallurgical control over the microscopic boundary between metals unlocked aesthetic possibilities that went far beyond uniform gilding. Nowhere is this clearer than in the dramatic bimetallic artifacts uncovered from the elite tombs of Sipán, where Moche rulers were laid to rest wearing elaborate regalia split precisely down the middle into gleaming gold and luminous silver. Among the most celebrated of these treasures is a massive ceremonial collar composed of 20 oversized peanut beads. 10 beads on the right side of the necklace gleam with the rich yellow radiance of pure gold, while the 10 matching beads on the left shine with the cool white luster of pure silver. In other funerary offerings, large crescent nose ornaments and radiating royal headdresses feature this exact same split along their central vertical axis, dividing a single continuous sheet of metal into two distinct, flawless halves. To achieve this striking visual duality, Moche metalsmiths did not solder two separate halves together, which would have left weak structural seams and visible join lines. Instead, they adapted the chemistry of replacement plating using selective resist techniques. The artisan began with a single, continuous copper substrate shaped to the desired form. Before immersing the object into a reactive chemical bath, the smith carefully coated the half intended to remain silver with an impermeable barrier, utilizing natural organic resists such as tree resins, molten beeswax, or dense clay slurries. When the partially masked copper piece was submerged into the boiling gold mineral solution, galvanic displacement occurred exclusively on the exposed copper surface, depositing a microscopic layer of metallic gold while leaving the protected half untouched. Once the first deposition was complete and thoroughly rinsed, the smith removed the organic resist using mild heat or botanical solvents, exposing the bare copper on the untreated side. The artisan then reversed the procedure, applying fresh resist over the newly gilded half and immersing the opposite side into an analogous silver mineral bath. In this silver electrolyte, composed of dissolved native silver minerals within a comparable chloride and nitrate matrix, silver ions underwent identical galvanic replacement with the underlying copper atoms. When the second resist coating was washed away and the entire object underwent thermal annealing in a charcoal hearth, the result was a seamless, unified copper artifact bearing an unbroken dual surface, pure gold on the right and pure silver on the left. This precise technical execution served a profound ideological purpose. In Moche cosmology, gold and silver were not merely precious commodities. They represented the fundamental cosmic duality governing the Andean world. Gold embodied the sun, masculine vitality, day, and the celestial realm of the upper world, while silver represented the moon, feminine creative power, night, and the watery underworld. By joining these two elemental forces across the exact centerline of a ruler's regalia, the metalsmith transformed the wearer into a living embodiment of cosmic balance, physically mediating between opposite poles of the universe through the invisible power of electrochemical replacement. The metallurgical superiority of this replacement process became even more apparent when these gilded and silvered sheets were subjected to severe mechanical shaping. In Old World metallurgy, applying gold leaf with animal glues or mechanical burnishing created a surface that could not tolerate significant plastic deformation. Any attempt to deeply hammer, stretch, or fold an object decorated with traditional leaf gilding would cause the surface layer to tear, blister, and flake away from the substrate, exposing the base metal beneath. Fire gilding using mercury amalgam suffered similar mechanical constraints, as the thick, brittle intermetallic layers tended to crack under heavy stress. Because the Moche displacement process relied on thermal sintering to create a true solid-state interdiffusion zone, the microscopic gold veneer was atomically bonded to the copper base. The crystal lattices of both metals were physically interleaved, creating a composite material that behaved as a single, extraordinarily ductile metallic sheet. This allowed ancient Andean metalsmiths to perform the entire electrochemical gilding process on flat, cast copper ingots before subjecting them to extensive cold working. An artisan could take a gilded copper blank and repeatedly hammer it on a polished stone anvil, reducing its thickness until it became as pliable as parchment without ever separating the gold skin from its copper core. This extreme ductility enabled the production of three-dimensional repoussé masterpieces that define Andean artistic expression. In the creation of elaborate feline headdresses, articulated royal crowns, and ceremonial masks, smiths placed the ultra-thin, pre-gilded copper sheets over carved wooden forms or beds of resilient pitch. Using polished stone hammers and fine hardwood punches, they chased intricate mythological scenes, embossed raised feline fangs, and sculpted deep relief contours into the metal. Throughout hundreds of successive hammer blows and repeated annealings in low-temperature charcoal embers, the sub-micron gold film stretched, deformed, and flowed in perfect unison with the underlying copper. When the metal cooled, the iconography remained encased in a continuous, unblemished skin of noble metal, free of cracks or peeling edges. The smiths could crimp the edges, pierce the foil with microscopic perforations to hang trembling sheet gold dangles, and fold structural tabs into complex volumetric forms. The electrochemical bond was so complete that the final sculpture appeared to be solid gold throughout its entire volume, displaying the surface brilliance of pure gold while retaining the structural toughness, springiness, and lightweight form afforded by the thin copper foundation beneath. The existence of these paper-thin gilded foils often leads modern observers to view the technique through a Western economic lens, assuming it was an ancient method for producing counterfeit gold or stretching scarce mineral wealth. In European metallurgical history, technological innovation was overwhelmingly driven by bulk mechanical performance, producing harder bronze for weapons, smelting purer iron for armor, and extracting massive quantities of bullion for commercial coinage. Gilding a base metal was frequently regulated by guild laws and royal decrees specifically to prevent fraudulent merchants from passing off brass or copper as solid gold. Within that framework, a gilded copper object was fundamentally an imitation, an illusion designed to mimic an expensive material at a fraction of the cost. In the ancient Andes, metallurgy operated under an entirely different cultural logic that archaeometallurgists define as a technological style. South American societies possessed immense natural reserves of placer gold and silver. Scarcity was not the driving factor behind their metallurgical developments. Instead, indigenous Andean ontology was rooted in concepts of material essence, transformative power, and the animate life force known in Quechua as Kame. Metal was understood not as an inert, static substance valued merely for its market weight, but as a dynamic medium that embodied the vital energies of the earth and the cosmos. The act of transforming a red, dull copper object into a radiant golden entity was not seen as a deceptive illusion, but as a genuine physical transmutation of the object's inner being. For a Moche metalsmith, the essence of an object resided within its surface, which was the active zone of contact between the artifact and the physical world. By saturating the exterior of a copper piece with pure gold through chemical baths and thermal sintering, the artisan was drawing out the sacred luminescence inherent within the metal, bringing its invisible potential into physical reality. The interior copper core provided the physical body, strength, and resonance, while the gold surface provided the spiritual identity and solar radiance required for ritual power. Far from being a cheap substitute for solid gold, electrochemical replacement plating was revered as the ultimate technical manifestation of sacred metallurgy. It demonstrated the smith's ability to manipulate the hidden properties of natural minerals, river waters, and fire to achieve a permanent, elemental metamorphosis. When an elite priest or warrior entered a sacred plaza wearing these glowing ornaments, the shimmering gold veneer was understood not as a superficial veneer hiding base copper, but as an authentic, energized manifestation of divine power radiating from within the metal itself. While archaeological context and metallurgical theory provided a compelling explanation for how these artifacts functioned within Moche society, definitive proof of the underlying chemical mechanism required rigorous empirical validation. To determine whether ancient Andean minerals could truly achieve this sub-micron plating without modern laboratory equipment, archaeometallurgist Heather Lechtman and her research team at the Massachusetts Institute of Technology conducted a series of controlled laboratory replications. The objective was straightforward: reconstruct the ancient mineral bath using only the raw chemical compounds available along the north coast of Peru and test whether it could plate pure gold onto modern copper coupons. The researchers formulated an aqueous solution combining natural desert salts in precise stoichiometric ratios: sodium chloride, potassium nitrate, and potassium aluminum sulfate. To this acidic electrolyte, they added fine gold powder. When the mixture was heated in open ceramic and glass beakers to temperatures between 80 and 95 degrees Celsius, the chemical reactions proceeded exactly as predicted. The nitrate and chloride ions, activated by the acidic bisulfate environment, reacted to generate dissolved nitrosyl chloride and aqueous chlorine, which rapidly attacked the metallic gold and dissolved it into soluble tetrachloroaurate complex ions. Before introducing the copper samples, the researchers neutralized the aggressive free acid by adding measured quantities of sodium bicarbonate and alkaline plant ash, raising the bath to a stable, mildly acidic pH. When polished copper coupons were submerged into the warm, golden-brown liquid, the transformation began instantly. Within 3 to 5 minutes, the bright orange surface of the copper darkened and then completely disappeared beneath a uniform, gleaming film of metallic gold. Spectroscopic analysis of the solution confirmed that copper ions were entering the liquid at a rate precisely balancing the gold ions precipitating onto the metal surface, proving that galvanic displacement was taking place without the aid of any external electrical current or wiring. Cross-sectional analysis of the laboratory coupons under scanning electron microscopy revealed a microcrystalline gold layer ranging between 0.1 and 0.5 micrometers in thickness, perfectly matching the measurements recorded from ancient Sipán artifacts. When the plated coupons were subsequently heated in an inert charcoal environment at 600 degrees Celsius, the porous microscopic gold crystals fused into a continuous, dense veneer. Energy dispersive X-ray spectroscopy across the metal interface showed the exact same atomic diffusion gradient documented in Moche masterworks, a smooth, continuous transition where copper and gold atoms had interpenetrated each other's crystalline lattices. Modern chemistry had conclusively vindicated the archaeological record, proving that ancient Andean smiths had perfected a sophisticated, reproducible system of electrochemical replacement plating centuries ahead of modern science. The roots of this sophisticated chemical tradition trace back centuries before the classic Moche era, emerging in the arid river valleys of northernmost Peru. Archaeometallurgical surveys of the Upper Piura Valley revealed that the earlier Vicús culture, flourishing from roughly 200 BC to 300 CE, had already begun experimenting with advanced surface enrichment technologies. Among the thousands of funerary offerings recovered from Vicús cemeteries, small copper nose rings, hammered sheet plaques, and animal effigies carry the unmistakable microstructural footprint of galvanic replacement plating. These early northern artisans were the first to recognize that submerging clean copper into natural salt brine solutions could selectively coat the base metal in a persistent skin of precious metal. Rather than an isolated stroke of luck, the technique represented an empirical metallurgical lineage passed down and refined through successive generations of coastal smiths. By the time the Moche civilization consolidated political and religious authority along the desert coast between 100 and 800 CE, electrochemical plating had transitioned from experimental workshops to an organized, high-output production system. Moche metalworkers operated at an industrial capacity, producing tens of thousands of gilded copper sheets, bells, crowns, and backflaps to equip an expanding hierarchy of priest-kings, military elites, and local administrators. The massive tombs uncovered across the Lambayeque and Chicama valleys demonstrate that Moche workshops maintained rigorous quality control over their chemical baths. Every batch of salt mixtures, water temperatures, and annealing times was calibrated to ensure that even the largest, most complex repoussé ornaments received a perfectly uniform, atomically bonded gold surface. When the Moche sphere waned, the specialized knowledge did not vanish from the northern coast. It was absorbed and reorganized by the Lambayeque and Chimu empires. In the sprawling adobe metropolis of Chan Chan, the capital of Chima, entire quarters were dedicated to metallurgical guilds. Chimu artisans inherited the northern chemical tradition and integrated it with southern metallurgical practices, deploying both depletion gilding for gold copper-silver alloys and electrochemical replacement plating for pure copper sheet metal. They produced towering ceremonial beakers, feather-shaped plumes, and massive wall panels clad in micro-thin gold coatings. When the Inca Empire expanded out of the Cusco highlands and conquered the Chimu realm in the late 15th century, the imperial state recognized the unmatched mastery of these coastal chemists. Rather than suppressing their techniques, the Inca forcibly relocated thousands of Chimu metallurgists to Cusco and provincial administrative centers across the Andes. In these state-sponsored workshops, the ancient northern tradition of chemical plating became a vital tool of imperial statecraft, transforming regional base copper tributes into gleaming solar regalia that adorned temples from Lake Titicaca to northern Ecuador. That continuous 2,000-year technological lineage came to an abrupt and catastrophic halt in the 16th century with the arrival of Spanish conquistadors. Driven by a relentless hunger for portable bullion, the invading forces viewed the vast corpus of Andean metalwork strictly through the lens of European monetary exchange. Beginning at Cajamarca in 1532, when Francisco Pizarro demanded a room filled with gold and two with silver as ransom for the Inca ruler Atahualpa, European smelting crews set up continuous metallurgical furnaces to reduce intricate indigenous masterworks into standardized rectangular ingots. The colonial smelting tallies preserved in the General Archive of the Indies in Seville reveal a profound and persistent European confusion. Spanish soldiers who hold massive piles of glittering crowns, breastplates, and ceremonial masks to the crucibles expected thousands of pounds of high-carat gold. Instead, as the artifacts melted, the microscopic surface veneers dissolved instantly into the molten mass, yielding ingots composed almost entirely of base copper. A single ceremonial shield that appeared to be solid gold would, upon liquefaction, yield only a negligible trace of precious metal. Unable to grasp the sophisticated electrochemical principles at work, European observers fundamentally misconstrued what they were seeing. Spanish chroniclers like Pedro Cieza de Leon and Garcilaso de la Vega recorded that native artisans possessed secret methods for coloring copper, but colonial authorities widely interpreted these techniques not as scientific mastery, but as deliberate deception. In European legal and economic frameworks, coating copper with gold was synonymous with counterfeiting and fraudulent alchemy. The invaders failed to understand that to Andean eyes, the microscopic gilded surface was not a commercial veneer designed to fool a buyer, but an ontological transformation that imbued the object with the sacred solar essence of gold. Because Andean metalworking guilds maintained their proprietary salt formulas and process parameters entirely through oral tradition and apprentice transmission, the destruction of indigenous social structures proved fatal to the science. When royal workshops were dismantled, master artisans conscripted into forced labor in the silver mines of Potosi, and sacred regalia systematically confiscated for the crucible, the precise chemical recipes vanished. The empirical understanding of natural nitrate salts, galvanic displacement potentials, and thermal diffusion disappeared from living memory, leaving behind only the corroded, green-stained artifacts that would puzzle modern archaeologists centuries later. Today, when the golden face mask of the Lord of Sipán gleams under museum spotlights, it no longer stands as an inexplicable paradox. What once looked like an impossible anachronism has been deciphered as a triumph of empirical chemistry. By harnessing the natural mineral salts of their desert environment, controlling galvanic potential gradients in boiling ceramic vessels, and locking the resulting veneer into place through solid-state thermal diffusion, ancient Andean metallurgists achieved flawless electrochemical gold plating centuries before the advent of modern electrical science. They did not need external batteries or conductive circuits. Instead, through rigorous experimentation with aqueous salt solutions, they directed spontaneous oxidation-reduction reactions to deposit coherent, atomically bonded films of pure gold across complex copper surfaces. This realization fundamentally overturns traditional assumptions about the chronology of technological innovation. Long before European chemists formalized the electrochemical series or constructed the first voltaic piles, pre-Columbian artisans had already mapped the practical behavior of ionic displacement. Ongoing archaeometallurgical research continues to demonstrate that ancient societies developed sophisticated physical sciences through rigorous empirical observation, arriving at advanced chemical solutions along entirely independent trajectories. Which aspect of pre-Columbian metallurgy surprises you more? The precision chemistry of their mineral dissolution, baths, or their cultural philosophy of atomic transmutation? If you want more in-depth explorations of forgotten ancient technologies, historical forensics, and the real chemistry behind humanity's greatest archaeological discoveries, subscribe to the channel. Ultimately, Andean metallurgical mastery was never an accidental byproduct of primitive trial and error, nor was it a superficial attempt to deceive. It was an advanced cultural science grounded in technological style, an ideology in which chemical transmutation infused humble base metals with sacred solar essence from the atomic level outward.